Welcome to The Explainer. I am so thrilled you're here today because we're going to uncover the invisible, yet completely mathematical forces that drive, well, absolutely everything around us. Whether you're marveling at a sleek electric vehicle accelerating down the highway, looking up at a massive wind turbine, or feeling your stomach completely drop on a towering roller coaster, there's a hidden language of physics dictating every single movement. And today, we're going to decode that exact language.
Okay, let's dive into this. On the surface, pushing a heavy cardboard box across your living room and riding a roaring steel roller coaster, they seem like completely different experiences, right? But here is the fascinating secret. The exact same physical rules of energy transfer govern both of those scenarios. In physics, the universe honestly doesn't care if it's a box or an amusement park ride. It only cares about force, displacement, and energy. To figure this out, we're going on a highly structured, logical journey today. Here's our roadmap. First, what is work actually? Second, potential and kinetic energy. Third, conserving mechanical energy. Fourth, power and work rate. And finally, efficiency in the real world. Don't worry, this isn't going to be a chaotic math lecture.
So, let's start with section 1. What is work actually?
In our everyday lives, work might mean sitting at a desk typing emails, or maybe thinking really hard about a problem. But in physics, it is a highly specific measurement that requires 3 strict conditions. Visualize yourself pushing that heavy box. First, a force actually has to act on the object. Second, the object must undergo displacement. Literally, it has to move. If you push a brick wall all day and get completely exhausted, but the wall doesn't budge, you've done 0 work in physics. And third, the force has to have a component aligning with the direction of that displacement. We measure all of this in joules, where 1 joule is equal to 1 newton of force moving an object exactly 1 meter.
The physical alignment of your force and the object's movement is absolutely critical here. If you push a box forward and it moves forward, that's positive work. The force and displacement are heading in the exact same direction. But what if you're pulling backward on a moving box to try and slow it down? Well, then the force acts opposite to the displacement, creating negative work. And if you're just carrying a box horizontally across the room, the upward force you exert to hold it up is completely perpendicular to your forward motion, meaning you're actually doing 0 work on the box itself.
And this brilliantly illustrates how we quantify it. Let's put some concrete numbers to this with an example from our source material. Imagine you're pulling a box across a smooth floor. You apply 60 newtons of force, and you pull it over a distance of exactly 8 meters. By simply multiplying that force and distance, we see that you have done precisely 480 joules of work. Bam! It's a direct, measurable transfer.
Moving right along to section 2, potential and kinetic energy.
Whenever you perform work on an object, you're actually transferring energy to it. Energy is simply the capacity to perform more work. The first flavor of this mechanical energy is gravitational potential energy. And this is just energy stored entirely because of an object's position. The higher you lift something, the more potential energy it has. Picture a 5-kilogram roller coaster cart being ratcheted all the way up to a 12-meter peak. Because Earth's gravity pulls down at 9.81 meters per second squared, that little cart is currently storing exactly 588.6 joules of gravitational potential energy, just sitting there waiting to be unleashed.
Now the second flavor is kinetic energy, the energy of motion. As soon as our roller coaster cart drops over that peak, all that stored potential energy instantly transforms into kinetic energy. The key factors here are mass and velocity. But notice that velocity is squared in this equation. That means even a tiny, tiny increase in speed creates a massive exponential spike in the kinetic energy.
Now what's really interesting about this slide is how quickly that kinetic energy scales up with heavy, fast-moving objects. Take a 1,200-kilogram car driving down the road at just 20 meters per second. Because we square that velocity, the car packs a massive kinetic energy of 2.4 times 10 to the 5th joules. Let me put that into perspective for you. That equals 240,000 joules of energy just barreling down the highway. Understanding this exact math is how engineers are able to design safe vehicle braking systems.
Next up, section 3, conserving mechanical energy. Here is the real narrative plot twist. Total mechanical energy, which is just the sum of kinetic and potential energy combined, follows a strict universal rule. The principle of conservation of mechanical energy states that if friction and air resistance are neglected, total mechanical energy remains entirely constant. Think back to our perfect roller coaster. Energy is literally never lost. It's just constantly changing costumes. At the very top of the hill, it's wearing the costume of 100% potential energy. At the bottom of the drop, it swaps costumes to 100% kinetic energy. The total amount of energy, the whole shebang, remains exactly the same.
And this continuous transformation isn't just for roller coasters. This perfectly illustrates how our modern world operates. In a hydroelectric dam, the potential energy of the stored water turns into kinetic energy as it falls, which is then transformed into electrical energy. An everyday electric fan takes electrical energy and turns it into the kinetic energy of its spinning blades. Even a simple torchlight takes chemical energy stored in a battery, turns it into electrical energy, and finally outputs light. It's the same exact principle everywhere.
Okay, Section 4. Power and work rate.
So, if energy is conserved and transforms to do work, what actually determines how fast a machine can accomplish that work? Well, power. Power is defined simply as the rate at which work is done. It's measured in watts, where 1 watt equals 1 joule of work per second. So, the crucial point is, if you have two machines doing the exact same amount of work, the machine with greater power is simply going to complete that physical work in much less time.
Let's illustrate this with a super quick calculation. Say an industrial machine successfully performs 8,000 joules of work in exactly 20 seconds. We just divide the work by the time. 8,000 divided by 20 gives us exactly 400 watts of power. That right there is the machine's work rate. Finally, Section 5. Efficiency in the real world. Let's move to and see how this builds when we face reality. Up until now, we've kind of been operating in a theoretical, perfect math world. But perfect energy conservation within a real physical machine? It's impossible. This brings us to efficiency. Think about it like this. If a real motor receives 5,000 joules of input energy, but only outputs 4,200 joules of useful work, it means it is exactly 84% efficient. A mathematically perfect machine would be 100% efficient. But in this case, 16% of that energy, or 800 joules, has somehow gone missing.
So where exactly did that missing 16% go? Well, the universe didn't destroy it. Remember, energy is always conserved, but the machine lost it to the surrounding environment. Real machines always have an efficiency of less than 100% because energy bleeds away. It's lost through friction between moving parts, heat generated by the engine, sound waves, and physical vibration. These are the harsh physical realities that literally plague engineers trying to design perfect systems.
But despite these energy losses, applying this work-energy theorem is literally how we build the modern world. Understanding how forces produce motion and how energy transforms allows engineers to design incredibly complex daily life applications. It's how we optimize the efficiency of hydroelectric power stations and massive wind turbines. It dictates the safety mechanisms of elevators and escalators. And it's the exact reason we can push for more sustainable infrastructure, maximizing the output of solar panels, electric vehicles, and biomass systems to dramatically lower our environmental impact.
Which leaves us with a truly provocative question to end on. As we continuously innovate with renewable energy and advanced mechanical design, trying to close that gap, will engineers ever completely overcome the fundamental forces of friction and heat to create a machine with 100% efficiency? Or is that 16% energy loss just a permanent tax we will always have to pay to the universe? Thank you so much for joining me on this explainer today, and I really hope this leaves you eager to look at the moving world around you through the incredible lens of physics.